Hey, this lecture we're going to finish up a section on viewing, and we're going to talk about shadows. And it may seem at first that what do shadows have to do with projection matrices and the kind of things we've been doing for the last few lectures. But it turns out if you're using a pipeline renderer, then getting shadows is a tricky business, but in fact you can do it by using your knowledge of projection and in particular perspective projection matrices. So I'm going to go over one classic algorithm for doing that and then look at a couple of others that will just look at the basic ideas, and then later when we talk about rendering to texture we'll be able to actually implement them, because the issues will be that many of these techniques for getting shadows will depend on doing multiple renderings, and if we do multiple renderings we need some place to store the results of the first rendering for those to use in the second, and so that's something we'll need to go a little bit further in the next after the next section when we talk about textures and rendering to texture. We'll fill out the picture. But at least this part you'll get an idea of just really how you can use projection to do many things. Okay, so let's start with this idea called flashlight in the eye graphics. And if you notice that if you look at most graphics, and especially look at the kind of graphics we're able to produce now, you won't see any shadows. Well, why don't you see any shadows? Well, one way to look at it is say, under what circumstances wouldn't you see any shadows just looking out at a scene in the real world? And the answer would be that only if the light source, let's assume one per ideal point source, was right in your eye or directly behind you, because then the shadow that was cast by objects that you're seeing would lie directly behind those objects as seen by you, and there would be no shadows. So the flashlight in the eye idea is that the light source, the flashlight, is right there in your eye while you're viewing it. But shadows are really important things to have in images, both for making them look real, but also from the point of view of trying to give visual clues to a user of your application. Shadows can be a tremendous help. This is especially important if you take something like a flight simulator and you have a pilot flying over terrain. The ability to see shadows either of his own aircraft or of objects on the ground is really helpful to try and navigate that airplane. And so we want to know how we can get shadows into our pipeline model when they're a global issue in the following sense, that you want to know if the surface is visible from a light source. How do you do that when you have many objects potentially in the scene, and that the light may be blocked from hitting that object by one of the other objects in the scenes? Well, that's kind of a global problem, because you need to have the objects around to be able to do that kind of a calculation. But we're using a pipeline renderer, and pipeline renderers work an object at a time. If you think back to some of those images I had at the beginning when we started talking about general approaches in the synthetic camera, and we looked a little bit at ray tracing, because it was a very natural way to look at things that was very close to physically just following rays of light. Shadows were generated automatically. When you followed a ray out from the viewer out to the object, you would then look at other rays called feeler rays that would go out and see if there were any light sources out there to illuminate that point. That's why they're called feeler rays. They're feeling for the light. But in order to do that, because those feeler rays might intersect something, then we need all objects that are available, and this is precisely what we don't have with a pipeline renderer, that we're rendering one line, one object at a time, one polygon at a time, and we don't have the others available. That's one of the benefits of it. In fact, we don't even know in general if we're rendering them in the same order every time. Now we can use some tricks, which we'll see in the first one will be projective shadows. Use our knowledge of being able to render polygons to be able to create what are called shadow polygons. We can also do some projective techniques, but most of the techniques will involve storing information. Now, there's one case you've seen where we do that when we do hidden surface removal. As we process object, object, object in a pipeline renderer, we store depth information in the depth buffer, and we can use that to do hidden surface removal. Well, we're going to see a very similar thing with some of the shadow techniques, where we store information as we render objects, and then we can put it all together to see where there are shadows. But these techniques will take multiple rendering passes. But let's look at the oldest technique, which is called Projective Shadows, due to Jim Blinn, who created many of the techniques we have during his career. He was at the Jet Propulsion Lab, and many of the early visualizations you saw of the early space probes and images of the planets were really done by him, and part of what he was doing actually was getting polygons. Also, the lighting model we're going to be talking about in the next few lectures was partly due to him. Okay, so some of these oldest methods come up, as I said, in flight simulators, where you want those visual cues, but those early flight simulators were basically very simple polygon models that did this kind of pipeline rendering, but with a limited number of polygons. So the idea was this, that if you have a polygon and you have an ideal point source of light, then the shadow of that polygon, and there will be a shadow somewhere. We may not be able to see that shadow depending on where we are, but there will be a shadow cast by that polygon from that light source, and that will itself be a polygon. So let's look at this in the next figure. So here's a light source, and here's the three vertices, and this little blue polygon, a triangle, is being projected. And let's assume that we have a flat surface, or we have a flat world. This might be something like a desert terrain where it's very flat. So we can extend this to any surface, but the equations, at least at first, are much simpler if we assume that the flat plane that the shadow falls on is the plane y equals 0. So this says, okay, look, the shadow of a triangle is a triangle. The shadow of another polygon is itself a polygon, and so I can actually compute this polygon, the shadow polygon. Now, how do I do it? Well, if you look at this diagram, you could say, wait a minute, that looks just like what you were doing at perspective, but you've done some kind of translation or rotation here to put the center of projection at the light source rather than at the origin. And in fact, that's correct. This is exactly what we do with perspective projections, and so it gives me a way of computing this shadow polygon, or more precisely, computing the vertices of this shadow polygon, and then I could add this polygon to my set of polygons, or for each polygon, I could now add its own shadow polygon, and now do a normal rendering, which will render the original polygon in its color, and render the shadow polygon in, let's say, black for a typical shadow. Now, notice I would have to do this kind of calculation for every polygon, and I'd have to do it for every light source, because if I had another light source over here, I would cast a shadow polygon over here. But this is eminently doable, so let's look at the process. So what we do is, if the source is at XL, YL, ZL, and one of the vertices of the polygon is at XYZ, we're going to cast the shadow onto this plane XP0 ZP, the plane Y equals 0, and I do that by doing a translation. Remember, this is again our strategy, which says, okay, convert everything to a problem you know how to solve, and do that by using some of our standard matrices. So if I translate the problem to where the light source is now translated to the origin, this is now looking like a perspective projection, given where these vertices of the polygon are. So that's exactly what we do. We translate the source to the origin by just the translation with the location of the point light source. Then I do a standard perspective projection for that, which will depend on what that y is, where the y of the light source is. And then I translate it back with t of xl, yl, zl, and that's basically it. Now I have the shadow polygon, and I could now render that polygon. So what I'm saying, let me say it slightly differently, what I'm doing by this derivation is getting these points over here. Where are they back in the space of the actual viewer? Because what I've done is I've done this calculation from the point of view of the light source. Now I'm translating it back to where these vertices lie in the normal space, and now I have this extra set of vertices which I can model. Or another way to look at the same thing is to say, what have you done here? You've done a translation followed by this matrix M, followed by the inverse of this translation. Use that to modify the model view matrix that you would be using for the blue polygon, modify its model view matrix by this matrix to get the appropriate model view matrix for the shadow polygon. And so here's what the process looks like. We put these two triangles onto the GPU, or just cycle through each one first. But think of it as two identical triangles. One is black and one is in whatever color it originally was. Or if you're doing shading and lighting, it has the shading and the shading parameters for that material. We compute the two model view matrices. The first one, and then which would be the normal one for the polygon, then the modified one using what we had on the last side. Send those two model view matrices over to the vertex shader where we do this. We'd use the first one to render the original triangle, the second one to render the shadow triangle, and this note here, the shadow triangle undergoes two transformations. It's the transformation which involves the light source location and then the original model view. And hidden surface removal takes care of everything else, because look here, if we look at this, suppose this polygon happened to be a little closer here, we'd see part of the polygon and part of the shadow, but that would all be taken care of automatically by doing hidden surface removal, because once you've computed the shadow polygon, that's just another black polygon which gets rendered like everyone else. So in fact, even if I look at this order, I can render those two triangles in the opposite order, and hidden surface removal will take care of it. Now, that looks kind of neat. Let me show you this, actually, before I go on. So let's look at that. Okay, there's an example. This is in the code for Chapter 5. It's just called Shadow. And what we're doing in this one is I'm rotating the light source. The light source is just going in a ring straight above the polygon. So this polygon is parallel, just to make everything easier, is parallel to the xz plane. It's y equals a constant, and the light source is kind of right above it, but it's rotating with a radius around and around. And you can see, first of all, that it's kind of working. There's the shadow polygon, and you can also see that the hidden surface removal is taking care of any kind of problems, of any kind of overlap. So that kind of projective shadow is very, very simple to do, but it's limited in what it's good for. So let's come back and discuss that and just briefly look at a couple of other techniques. So the problems, it works great if you're just doing shadows on a single flat surface. If I want to change that surface, and it's just one surface, it just makes the trigonometry and the equations slightly more complex. That's not too big a deal. If you have a real terrain that you're projecting it on, where think of the terrain is broken up into a lot of polygons, each of which have a different orientation, then it starts getting tough. It also, the really difficult problem is if you have an object, say, so suppose I had a cube, or let's say, suppose I had that single polygon and I had a cube sitting on the ground, and now that as the light source moves, the shadow is falling partly onto that cube and partly onto the ground and partly onto a couple of different surfaces of the cube. Well, that computation is possible, but but a lot more complex. And at that point you start saying, well, I really want to look at some other methods. So let me just sketch out 3 other methods, all of which to some degree involve an understanding of projection. One technique that's not quite yet in WebGL, although I think you could probably create this yourselves by just coding it and not expecting the functions that were in desktop OpenGL to be there. What this thing did is use 4-dimensional textures, but the idea was very simple: is to think of a shadow as some sort of projection coming out of a slide projector. And the idea was to put in that slide projector an image as a texture map that would do the shadowing. And this so it's sort of the projective kind of technique, but it's using an image, and you might have to compute that image by a separate rendering, but you can do some wonderful effects with that, and that will tie in with when we start talking about discrete things in a week or so, with things that we can do to get global illumination, like projecting clouds onto a shiny surface. These kind of techniques are available. But I think of a projector, a slide projector, as being just another projector from the light source, and if I put the right image in there, I can get on the ground the kind of things I want to see, like shadows. Now, shadow maps are more interesting, I think, and they're partly because they're very doable with multi-rendering, but the basic technique we can understand from this. So come back to this slide. Let me look at a picture of this first. That here's a viewer sitting over here, and here's a single point source. Here's a polygon, and if we look at the shadow, we can argue that the way that we can tell that this point is in shadow and is not lit is because the distance from the light source to the blocking polygon is shorter than the distance from this viewer out to this point. And these are just, in a way, if we go back to the last technique, these kind of views are just the views from 2 different points of view, the view from the light source location and the regular view from where the viewer is. So what I can do is first compute the view from the light source. And I can do this, and I want to save this, because what I really want out of that view is not particularly the image, but I want to know how far everything is from that viewer. Okay, I want to know how far this point is on the polygon. I want to know how far this point is. Well, where do I get that information? Well, the answer is I have that information because it's in the depth buffer. So what I want to do to get this information is to do a normal rendering from the point of view of the light source first and compute what's sometimes called the shadow buffer now. And it will have all those distances. And I'll also note that this rendering could be very, very simple. It doesn't care what the colors are of these polygons. It doesn't need to worry about complex lighting reflection models at the surface. It simply wants to know what is it hitting first. So I can compute that, and generally what I'm going to do is store that in off-screen memory, which in a modern system is somewhere in texture memory, and that's the part that we'll be studying a little later. But I like to present this here because when you look at it this way, you see it's really just 2 different projections, and I somehow have to combine them. So that's the idea of a depth map or a shadow map. And again, we don't really care about the image. We only care about the distances that are in the depth buffer. And I have to do that, obviously, for each source. Now, what is any problems here? Well, besides that, I have to do these multiple renderings. I'm looking at things from 2 different points of view. So in that sense, I'm in 2 different coordinate systems. I've stored the information in a texture map. Well, that's discrete information. And I have to convert whatever I do in this light coordinate system over to the viewer's coordinate system, so these distances and locations are making sense. And that will lead to some aliasing issues when you do this, but in the final rendering, you're really just comparing these distances with all of these shadow maps that you've computed in previous rendering. So if and if the depth is less, you're going to put it in shadow. If otherwise, you're going to use the rendered color. So this technique requires multiple rendering. Again, we're going to come back and look at this when we look at render to texture in a couple of weeks, which is a very, very powerful way to do this. And you can do renderings on very large numbers of polygons very, very quickly. So these kind of techniques actually work remarkably well now. And I can show you at that time that the work is being done in the shaders, that you do a very basic computation of once you know where the light sources are, and you can just put that information in the shader. If the light sources are moving, move them in the shader, and everything is done in the vertex and fragment shaders. Now let me give you one more image of a slightly different view where we're doing sort of conceptually the same sort of thing, but we're going to use the information a little bit differently. So suppose here's our standard view. Here's a perspective view. Oh, by the way, I should have pointed out all along, if you have a distant source, what happens in all of these techniques? Well, if the light source goes off to infinity, kind of like where the sun is, what happens? It's just like a standard projection. When you move the center of projection out to infinity, all of these projectors become parallel to each other, and the direction of the center of projection is replaced by a direction of projection. And it's an exercise in the chapter to figure out how these matrices change when you're out here at infinity. And in fact, it's a very straightforward change to do it that way too. So coming back now to this ideal point light source here. Here it is projecting a simple triangular polygon and is casting a shadow. Now let's look at this in terms of the view volume from the standard center of projection. So here it is. Here's the front clipping plane, the back clipping plane, and this is the frustum in here, where everything in here is it won't be clipped out. But if I now look at the intersection from this diagram, what is this doing? This is sort of an infinite pyramid going out from the light source, determined by the shape determined by this polygon, and everything behind it is in shadow. So if I now look at this volume intersecting this other volume, everything is composed of flat planes, and you have to use I couldn't draw this very well, but everything where the intersections meet is determined by flat planes. And if you know those flat planes, then you could argue when you're moving along a projector here, suppose I'm looking at some point, I look at a direction going through a pixel and going, say, along this line, I start intersecting various planes where the first one over here would be, I'd be entering a shadow region, and then there would be a corresponding place over here where I would leave the shadow region, and then when I'm outside of the shadow region, I'm not in shadow. So by computing this more complex volume, or at least computing these planes where I enter and leave shadow, as I do my normal rendering, I'm looking at those planes and going in shadow, out of shadow, in shadow, out of shadow. If I have multiple light sources, then I have many planes in here. So the shadow volume is another way of doing it. And what are you saving? You're actually saving these intersection planes to determine when you're going in and out of shadow. You have the same issues with two different points of view, or many different points of view if you have multiple light sources. So you have the same issue about having to convert everything into the same coordinate system and do some saving of information because you have to compute these volumes. So this is another way of using the same kind of projection ideas to give you kind of an unexpected technique. Okay, so now we're going to turn to lighting and shading, and we'll actually be using some of these things a little bit later.